Good morning, plate tectonics. Plate tectonics is the unifying theory of geology, meaning it's like the big idea of geology, just like evolution in DNA would be for biology or um, relativity for physics. So it is the basic knowledge of geology. So we'll go through that now. All right, little background information. The Earth, recall, um, differentiated. And during that differentiation, the denser atoms moved to the center of the earth and became the core. The mantle then was a little less dense, has lots of magnesium and iron versus iron, nickel in the core. And then there's the crust that is a silicate based, less dense rim of the earth. So those differences are differences with composition. But there's another way that we can look at the layering of the earth, and that is the strength of the layers. So that's here. The strength of the layers varies. So the outside of the earth is rigid and strong. As we go to the mantle, there's a zone where it gets weaker and can flow when there's stress put upon it. Then the outer core is molten and the inner core is solid. So we'll focus on that strength difference. The two layers then with the strength difference near would be the lithosphere and the asthenosphere. So the lithosphere includes the crust and the upper mantle. So I'm going to go back one. So here we are at the crust and the very upper mantle. So right about here is a zone where the layers go from being rocky to flowing when there is stress put on them. It's moldable ductile solid, so it's not liquid. It's just hot and can flow when you push on it. And that is the asthenosphere. The lithosphere is broken into what we call plates. So those rigid outer plates are cracked and they fit together kind of like a puzzle. We'll see some figures on that in a minute. Every place on Earth can be defined by its plate. So I live in Boone. I'm on the North American plate. I think probably most people in this class are on the North American plate. These plates move around the earth a few centimeters every year, and they move on top of the flowing asthenosphere. And we use the term convecting. There's a convection cell where hot material rises and cool material sinks. And those are that's convection, rising and sinking. There are about 12 plates. There's a convection cell. So if you have a source of heat, this is like a burner on a stove and a pot, then the hot stuff at the bottom, say this is water, is going to be less dense as it heats up. The molecules move further apart, and that material is going to rise. When it gets to the surface, it's going to cool down. Those molecules get closer together again, it becomes more dense, and it sinks, and the process continues. So that is convection, and where it sets up with two convecting areas kind of mirroring each other, we call that the convection cells. So let's take that image from a pot and take it to the earth. So here is a cross section through kind of a cartoon of plates. And the convecting cells within the asthenosphere, hot magma is going, hot is not magma. Hot material is going to rise and cool material is going to sink, and it's solid. When that happens, it pulls these plates apart. When that happens, there's going to be decompression at that point, and that decompression promotes melting, and then we have magma come out, and this is a mid-ocean ridge. On the outside of that, over here, this plate is what we call subducting underneath this other plate. So we have three plate boundaries here. 1, 2, 3. So we have those convection cells dragging the plates along. There are three kinds of plate boundaries. That's interactions between the plates. The plates are either going to be moving towards each other or away from each other or sliding side by side. So the interactions at those boundaries and the mechanisms for moving the plates is all the basis of plate tectonics. So here is a map of the plates. The arrows on the map are vectors with the length of the vector relative to the speed of movement of that plate, the velocity of that plate. So long arrows are quick moving plates and the shorter arrows are slow moving plates. So you can see a 5 centimeter per year arrow, like here on the Australian plate. That's a pretty long arrow. But a lot of them, like around North America, are a little bit shorter. There's a little bit of rotation in here. So those are the plate movements. The plates are labeled on here. So in the middle is the big Pacific plate. The North American plate, notice it covers Greenland, it borders Iceland, it goes up through over to Russia. So the North American plate's pretty big. The Antarctic plate wraps around Antarctica. Okay, so I won't go through all of them. The Eurasian plate is also pretty big. So those are the plates. How did geologists figure out plate tectonics? One of the first things that was realized is that the continents could be put together like a puzzle. And when you move those puzzle pieces together, there was a realization that rock types matched up. So across the northern North America and Europe, there were matching rock assemblages. Assemblages means it wasn't just one rock type, it was a group of rocks. Rocks matched up across northern Africa and South America, and then also across southern South America and the area of South Africa. The early idea then was that there was something called continental drift. And continental drift was proposed that the continents moved around, but there was no mechanism for how they moved. And this was based on those rock types matching up and glacial evidence matching up and fossils like this Mesosaurus matching up. So the glaciers, the fossils, these rocks and mountain chains matching up. And the idea then was that the plates just kind of plowed around through the ocean basins. So nobody really bought into that. It wasn't until later that this idea of something called seafloor spreading, that the ocean basins in World War II, they worked this out. Harry Hess, that he was in the Navy and he went around the ocean basins figuring out the bathymetry and the topographic highs and lows of our ocean basins. He realized that there were things like the Mid-Atlantic Ridge, a giant mountain chain in the middle of our oceans. And that became the mechanism then for how ocean basins spread apart. And then it was realized that there were deep trenches on the edges of our ocean basins, and those trenches would be where the oceanic plate was going down and being consumed. Okay. It was 1929 when Arthur Holmes put forth, he was kind of a geophysicist, that there were these convecting currents, that there was flow in the asthenosphere of the solid material, and that the convecting currents would be dragging the plate one way or another. And he also, Arthur Holmes, put together the ideas of these supercontinents where there are punctuated points in geologic history where the continents came together. So this would be like Pangaea, Gondwana. So in World War II, when they're mapping the seafloor, discovering things like these giant mountain chains and realizing that earthquakes matched up with all the little black dots on here are earthquakes. The earthquakes activity matched up with the mountain chain. So earthquakes mean there's movement. So some movement was happening and there was a topographic high. They found similar ridges in the Pacific and in the Indian Oceans. Okay, so Harry Hess, the name I just mentioned, he was in the forefront with Robert Dietz of saying like new crust was perhaps being formed at the mid-ocean ridges. There was a Canadian geologist, and he was looking at the evidence on continents and also the new evidence from the seafloor, and came up with this idea that over time, ocean basins actually just opened and closed. There was a cycle to that activity, and that now is called the Wilson cycle. Okay, so in 1968, this is really when the shift happened in kind of believing in this concept and grasping that evidence of plate tectonics, where earthquake activity and volcanic activity were along these mountain chains in the seafloor, and that there were unique places at our continental margins where there was plate tectonic activity. So around 1970 is when the new textbooks were published that said, plate tectonics is a thing. So here, let's shift ocean basins. This is the Pacific Ocean Basin, and this is the Ring of Fire. The Ring of Fire around the Pacific predates June Carter Cash and her Ring of Fire. So this Ring of Fire, all the black dots are earthquakes, and all of the red dots are volcanoes. So we have a lot of volcanoes over here in North America, lots of volcanoes down in Central America, and all along the Andes in South America, throughout New Zealand and the island nations in the South Pacific, up through the Philippines and Japan and into Russia, and all along the Aleutian Island arc here off of Alaska. Okay, so that's the Ring of Fire. And in those locations, the oceanic crust is going underneath either older oceanic crust is going underneath younger oceanic crust, or it's going under buoyant continental crust.